for quadratic, cubic, square root, and cube root? Everybody good? Yes, there's a place to turn in. How about this square root? Did you guys get the end behavior for square root? Square root was the one that looks like this. So in behavior on this one, this is the only one that's a little bit different, so I do want to talk about it for just a second. Several people asked me about it yesterday. As x goes to infinity, so as I look to the right side, I'm going up. It's not as fast that I'm going up, but I'm still going up nonetheless. But then the left side is the one that should give you a little problem, or might have given you a little problem. So I say as x goes to, and this time it doesn't go to negative infinity. The graph just stops right here. So I say as x goes to 0, what happens to the y value when x is 0? It goes to 0 also. So that's what the end behavior looks like on that one if you didn't get it. Everything else was pretty straightforward. Any questions? Any questions? What you mean? It's still creeping up. You're talking about the graph itself. It's still going up. So if I'm at like 4, I go to 2. 16 would be up to 4. So it's going up. It's just not going up very fast, but it is going up. It's actually still continuous, even though it doesn't go on forever here, because you can draw it without, for our definition anyway, so far, it's continuous. Any other questions? All right. Brace yourselves. I know. Well, a lot of times whenever I say that, then it's not as bad, or doesn't seem, but we're into transformations full on today. We will spend the rest of the week on transformations. The homework that I'm giving you today is extensive, and it will not be due until Friday. So you'll be working on it. There's roughly 50 problems in the packet, I think. But we'll work on it as soon as we finish going over things today. We'll do several examples, and then we'll get started on that. We'll work on it for the most part tomorrow too in class. So it'll be 2 nights worth of homework plus a day and a half of classwork to get it done. But it's that important, and that's why I wanted to go through this way. And it's also what your project will be based on. So are y'all ready? Ready or not? I'm going to need y'all to be just a little bit more excited. Thank you. So I'm looking at your packet. I'm going to take you through the very last page here, and then I have a different packet that I have used for several years with transformations. The numbering on it is off, and I know that, so if you're OCD about that, I apologize. Never went back. It took so long to make it, I never went back to fix the numbers. All right, so if you look on the left, we're going to use the parent function of the absolute value as kind of a guide on what we're going to compare to. So I want you to look, and this is just an introduction to transformations here before we get into the rules. So the parent graph for the absolute value of x is f of x equals what? What's the parent function? The absolute value x, right? Are we all okay? That parent function we talked about yesterday, we will be talking extensively about linear, absolute value, and quadratic parent functions and their transformations. Not so much anything else just yet. All right, so if I graph this is the one that's 0, 0, 1, 1, negative 1, 1, and it V's off like this. Now, the directions on here say to use your calculator to graph, but what I want to do is have us graph them by hand quickly on here and see what happens as these different things happen to the graph. So number 1, and I'm going to do this in a different color. We'll do this in green. F of x equals the absolute value of x plus 2. So if I graph this the way that I know to graph this, the first thing I find is the what? The x part of the vertex, right? What's the x part of the vertex here? -2, right? X plus 2 equals 0. I said equal to 0 and solved it, so -2. Plugged in, I still get 0. And now I go 2 up, 2 down. -1, 0, -3, -4. When you plug in -1, what do you get? 1. How about 0? 2. How about -3? 1. It's -1, then we make it positive because of the absolute value. How about -4? 2. Okay, so let's graph this, because what we're going to do is we're going to compare the parent to this green one and see what happens, see if we can make kind of a connection here on what's going on. So -2, 0, -1, 1, 0, 2, -3, 1, and -4, 2. How does it look different? It looks literally like I just slid it over, right? In fact, it looks like every point just slid over how many? Looks like they all slid over 2. Do you agree with that? This one went over 2. This one went over 2. This one went over 2. Look at the equation compared to the parent. Everything moved left 2. You agree? Everything just slid. The red or the pink became the green, and to get there it was. So let's see if we can make another conjecture. Number 2 tells us, y'all got that? Numbers. The second one tells us, and we're always comparing to the parent. So I'm going to just throw this parent up here quickly. And instead of doing 2 on either side, I'm just going to start doing 1 to make this save us just a little bit of time. This is the parent, right? That's absolute value. And number 2 asked us to do the absolute value of x minus 2. Where's my vertex? +2. And I get 0. And instead of going 2 up, 2 down, let's just go 1 up, 1 down, just for the sake of time. So 1 up would be 3, 1 down would be 1. And it looks like I get 1 for both of those. So 2, 0, 3, 1. What's happened here? I moved to the right 2. Interesting, interesting. Wonder if it makes a difference if that +2 or -2 is outside those absolute values, like number 3. Here's my parent. And now number 3 says f of x equals the absolute value of x plus 2. Where's my vertex? 0, 2. 0, 2, because I set that equal to 0, and then I plug in and I get 2 back out. Now 1 up, 1 down, so let's go negative 1 and positive 1. What do you get? 3. 0, 2, 1, 3, and negative 1, 3. What happened? It moved up. It looks like 2. Every point moved up 2. Have y'all done any transformations before? No, yes, some. Make a guess, make a conjecture. What do you think is going to happen if I change that plus 2 to minus 2? Oh, it's going to go down. Down from where? Down from the red or down from the purple? Always from the purple. It's always from the purple. So if I did minus 2, in fact, watch how much quicker. If I know that parent graph right off the top of my head, I can just move all these points down to and if you do your t-chart, you'd see the same thing, 0, negative 2. Give you just a second to catch up, because those are the easy ones. 5, 6, and 7 are when we get into it a little bit harder. Yep. I'm going to just sketch a parent here. Yep. Which one's number 2? Oh, no. There you go. Was anybody not here yesterday and didn't get a red sheet? All right. Did you get all those? Okay. All right, on to 5, 6, and 7. For number 5, we have f of x equals 2 times the absolute value of x. Where's my vertex? 0. And when you plug in 0, what do you get? 0. Now let's go 1 up, 1 down and see what happens. Let's go negative 1 and positive 1. See if we can see what happens. When it's 1, what's my y value? 2. When it's negative 1, what's my y value? 2. So instead of 1, 1, it's now 1, 2, and negative 1, 2. what does it look like happened to my graph? It got skinnier. It got skinnier. It looks almost like if you took that x-axis and pushed it in, or if they were rubber bands and you took that y-axis and stretched it out, right? So I will call this sometimes a horizontal, actually let's call it the vertical since it's a vertical stretch, meaning that graph just stretched out vertically, okay? And that's what's happening when I'm multiplying in front like that. We'll talk about each one of these. How about number 6? Where's my vertex? Still 0, 0. Let's go 1 up and 1 down. What do you get? 1/2. That's exactly right for both of them. 1, 1/2, 0, 0, and negative 1, 1/2. It got wider. That's exactly right. So if the green I said was a vertical stretch, what do you think the blue might be called? Let's still call it vertical. But what's happening? It's not stretching it out, squishing it in, right? So I'm going to call it a vertical shrink. Notice what happens. As this number in front gets bigger, what's happening to my graph? It's getting skinnier, right? And as this number in front gets smaller, my graph's widening up. That's exactly what we saw with our quadratics. Remember when we talked about that A in front and what it did? Up, down, skinny, wide. Same thing that's happening here. Last one, and I'm going to put this on the same graph here, and you'll see why. You're exactly right. I've got negative absolute value of x. I'm still at 0, 0, but let's go 1 up, 1 down. What happens? What do I get there? Negative 1. That negative in front is forcing everything negative. 0, 0, 1, negative 1. So it looks exactly the same, but what happened? It flipped. It flipped. Or reflected over that x-axis. So we're going to talk about some very general rules in here, and then we're going to talk about the red sheet, which gives you a lot more specific rules and how to find these different things. All right, transformations guide. Hopefully this makes sense to you since we did an example of each of them now. The first one says f of x plus h. Okay. Now understand that means I am adding something to h. So this looks a lot like numbers 1 and 2 that we just did. Okay. It's hooked to the x. So if I'm talking about a quadratic or an absolute value, it's hooked in with that. For example, if f of x is x squared, this would look like, then f of x plus h would be x plus h squared. That number goes inside, hooked to the x. If that happens and you're adding a number, what did it do to our graph like in number 1? Look at number 1. It moved it left. So this moves it left h units. For example, if you want to put a little example in there, if f of x equals the absolute value of x plus 6, what does that mean? I've moved it how many from the parent graph? This is moved left 6. I would just take that parent graph and slide it left 6 times. Y'all okay? The next one is f of x minus h. Okay, again, this is hooked to the x. What happened when I subtracted something like in number 2? What did it do to the graph? It moved it right h units. So again, if that was f of x equals the absolute value of x minus 4, that would be right 4. If it was x minus 1 squared, that would be that parent parabola, but shifted right 1. We're always going back to the parent here and doing the transformation. How about f of x plus some value k? So in other words, the whole equation, and then on the end, you just add something to it. It moves up. You're exactly right. Up. Okay. So for example, and I'm going to use this one as an example to show you the difference. Notice when it was in parentheses, it moved right. Now it's not in parentheses. Oops. Plus. We want a plus. Now it's not in parentheses, which means it's going to be moving it up or down, not left to right. So this is up. Yeah. Do you see the difference there? And then, of course, if I subtract, what's it doing? Going down. Translations, or slides as we call them sometimes, are the easiest to do. Let's say this was the absolute value of x minus 3. That would be down 3. Everybody okay? I'm going to come back to dilations in just a second. Let me just make sure you understand. What would this graph look like? And I'm going to put the parent one on here so you can compare. But what's happening? It goes to the left one. I don't have to do a T-chart. I don't have to do any of that. I just have to look and go, oh, wait, this means I go left 1. So I'm just going to take every point and move it left 1 and graph. Can you do more than one at a time? Say yes. What if, let's do a quadratic. Tell me what's happening here. Remember, I'm comparing to the parent, so let me just sketch the parent here. Tell me what's happening. You're exactly right. I'm going to move right 2 and up 1. So every point on this graph moves. Right 2, up 1. Right 2, up 1. Right 2, up 1. Y'all see what we're doing with the slides? Are you sure? Yeah, if you want to flip over to the back to write that down somewhere, feel free. You might need it because these are multiple transformations, so they get a little bit harder. Bless you. Let me see if you really understand. Y'all still copying? What might be an equation for this graph? F of x equals, we know it's absolute value, right? How did it slide? Plus 2. It slid left 2 and up 1. Does everybody see what I did there? How I wrote that? Y'all have got this. I'm so impressed. I was so worried. All right, y'all ready to talk about dilations? Dilations are just a fancy word that means shrinks and stretches. This is a very basic dilation description here. We're going to go into a little more detail whenever we get to your red slip, but for right now, we'll stay basic and then we'll talk about it a little more. Yeah? Tell me when you're done. And stretches. So the first scenario we have is some value A multiplied out in front, and it says when, when the absolute value of A is bigger than 1. Now we said absolute value because it's a little bit different if I just make it negative. We know that does something else. But as A gets bigger, what did we say happens to the graph? It gets skinnier. So give that to me in terms of a vertical something. A vertical stretch. And the reason that I say that is because if we think about it getting skinnier, what if it's not a V or a parabola? What if it was like the cubic we talked about? What would that look like? So if you can envision that y-axis just stretching out and what it does to the graph, it'll help you understand what that vertical stretch does. But if you want to remember skinnier also for some of yours, that's fine too. And then the other one says when, and this one's a little bit harder to understand, but because we've already done quadratics, what kind of numbers am I talking about? If it's absolute value, it's always positive. So what kind of positive numbers are less than 1? Decimals and fractions, right? 1/2, 1/4, 1/3, those kind of things. So as that number gets smaller, what's happening to the graph? It's getting wider. So it's a vertical shrink, which produces a wider graph. If I just smushed it in. Everybody okay there? I'm going to go ahead and do reflections before I pull it all together. So this says, and I want you to add one more on here that we'll do in just a second, but it says negative f of x. And what happened on number 7 when we just threw a negative on the outside? Reflected. This is a reflection over the x-axis. And I told you I wanted you to add another line on here, and the reason is we can also make x negative, and that reflects over the y-axis. I'm going to give you a brain break for just a second before we move into the red sheet and how we're going to tie this all together. So if you need to run to the bathroom, translations, which are the slides, and tomorrow we'll really delve into the dilations, which are the hardest. But I want to go over this red sheet with you for just a second and tell you how you can use it to help you as you try to find points. So if you look, you'll notice that it's similar to what you have on the sheet we just filled out, but it's a little bit different. I added an extra column in there to help you. So for instance, on the first one, you have f of x plus c. And that's the function notation. That means you can take any function, and this doesn't just work with parent functions, this works with any function in the world. If you have a function and you add some number to the end, it takes that original function and it moves it up this many units, okay? So the transformation, the middle column tells you what it's doing, and it says that this is a vertical translation, and translation is one of those geometry words that just means slide, right? So it's a vertical translation up C units. And then there's this change column over on the right, and this is the one that'll be the most beneficial to you, especially especially in the dilations whenever we get there. So it tells you that xy, okay, so this would be on the parent graph or on the function graph that you're looking at. Xy becomes x y plus c. Now what that means is that every point on your graph, let me just show you, if I had the absolute value, here's my parent, and I wanted to say f of x equals the absolute value of x plus 1. We know that that means slide up 1, right? This point is 0, 0, this point is 1, 1, this point is negative 1, 1. Well, sliding up 1 just means that every y value, for every point on my original graph, I take it and I add 1 to the y. So this becomes 0, 1, 1, 2, and negative 1, 2. So I know that that's pretty easy to slide, but yeah. But do you understand the notation here and what we're doing? Because that's what's going to help you graph the dilations a lot. Okay? So you're just adding, by adding this to every y, it's moving it up. Okay? And so you notice then you've got the one that goes down, which is the subtraction. The next one is your horizontal left and your horizontal right. You've got the two reflections. Now notice what changes there in the reflections. Look in your change column. If you reflect over x, you're changing y. And if you reflect over y, you're changing x. And then, of course, your dilations, which are the last ones that we will really hit on tomorrow. But I wanted you to understand how to use this to help you because it will be a lifesaver to you as we go through. So now look at your packet. So I'm going to work through an example of each kind with you now, and then I'm going to set you loose on it. But for tonight, I want you to be at least through number 22 for when you come in tomorrow. The whole thing on Friday. Yeah, the whole thing on Friday. Yes, there's a place there. No, just one. It's a 10-point assignment since it spans 2 nights, and so you'll just turn in one time. Look at number 1. We'll do this one together. You might have to kind of squint a little bit, but it says for each graph, identify the parent function, describe the transformations, write an equation for the graph, and identify the vertex and describe the domain and range. So that's a lot, right? It's a lot of stuff for each one. So number 1, parent function. What is the parent function of that graph? That is an absolute value. You are absolutely right. Parent function is the absolute value of x. Now it says, what are the transformations? In other words, how has it moved from this to what it is now? And I want you to tell me in words what it's done. It moved right, how many? Right, 2, and then it did what? Down 5. Those are the transformations you're going to list. That's how it changed from the parent to what it is now. Now it asks you for an equation. Well, what's the equation? If I start with this and I go right 2 and down 5, what's my new equation look like? Exactly right. What's the vertex of that graph? You notice something about that, by the way? Yep, that's exactly right. How about the domain? That never goes away. Negative infinity. How about the range? That's right, negative 5. I think y'all are going to get this nicely. Let's flip over to number 10. Yeah, knock on wood. Yeah, I hope so. We're starting easy. We're starting with the translation. As I kept talking, I was like, this is a lot. We'll stop with the translations today. Number 10 is in a little bit different form. You're given it in words and then asked to write an equation and graph it. So it says that it's a quadratic function. So what's the parent if it's a quadratic? X squared. Translated up to and right for. What is that going to look like? What's that equation going to look like? X minus 4 squared. Now move it up 2. Now, I'm going to graph this, but even though this is vertex form, bless you, that we learned to graph in, we're not going to graph it that way. Instead, we're going to graph it by sliding it. So we're going to start with that parent, And remember the parent of the quadratic, the same 3 points, but it's curved like this. And it's going to slide right 4 and up 2. 1, 2, 3, 4, 1, 2. 1, 2, 3, 4, 1, 2. You don't have to graph the parent, no. You don't have to graph the parent. I was just showing you how it moved there. What's the domain? That's absolutely right. How about the range?
Good morning, Camden High School. Please stand and join me for the Pledge of Allegiance.